Hello everyone, in this video we will see what beta function and gamma functions are, their properties, and establish a relationship between these two functions. So let's start with the beta function. The beta function, also known as the first Eulerian integral, is written as beta m comma n equals to integral 0 to 1 x to the power m minus 1 times 1 minus x to the power n minus 1 dx, where both m and n are greater than 0. So this is the beta function, and its properties are, the first property is beta m comma n equals to beta n comma m, and the second property is beta m comma n equals to 2 times the integral 0 to pi over 2 sine 2m minus 1x times cos to the power 2n minus 1 x dx. So these are the two properties of the beta function, and we will prove both of them. So to prove the first property, we have beta m comma n equals to integral 0 to 1 x to the power m minus 1 times 1 minus x to the power n minus 1 dx. Now we will use a property of integration, that is integration 0 to a f of x dx equals to integration 0 to a f of a minus x dx. So the limits are same, 0 to a, and here also 0 to a. The only change is, in place of x we have to write a minus x. So let's do that. In our case a is 1, so 0 to 1, and in place of x we have to write a minus x. So in our case it will be 1 minus x to the power m minus 1 times 1 minus, and in place of this x also we have to write 1 minus x and whole power n minus 1 dx. 0 to 1, 1 minus x to the power m minus 1. So 1 minus 1 is 0. So we are left with x to the power n minus 1 dx. Beta m comma n equals to integral 0 to 1. So we can rewrite it as x to the power n minus 1 times 1 minus x to the power m minus 1 dx. So if you see here, we have x to the power m minus 1 and 1 minus x to the power n minus 1. So we wrote m comma n. So here m and n have switched their roles. So we can write beta n comma m. So we prove that beta m comma n equals to beta n comma m. So for second proof, we have beta m comma n equals to integral 0 to 1 x to the power m minus 1 times 1 minus x to the power n minus 1 dx. So all we have to do is substitute x equals to sine square theta. Now differentiate both sides with respect to theta. We will get dx equals to 2 sine theta cos theta and d theta. Now since we changed x in terms of theta, we will also have to change the limits in terms of theta as well. So put x equals to 0, we will get theta equals to 0, and put x equals to 1, we will get theta equals to pi over 2. So our beta function becomes beta m comma n equals to integral 0 to pi over 2. So instead of x we have to write sine square theta, sine square theta and whole power m minus 1. And here also we have to write 1 minus sine square theta whole power n minus 1 dx. Now in place of dx we can write 2 sine theta cos theta d theta. So 2 sine theta cos theta d theta equals to, we can bring this 2 in front, 2 integral 0 to pi over 2. Now multiply these powers, we will get sine to the power 2m minus 2 theta times 1 minus sine square theta is cos square theta, and multiplying the powers we will get cos to the power 2n minus 2 theta times sine theta cos theta d theta equals to 2 integral 0 to pi over 2. So since this and these are like terms, we can add their powers. Sine 2m minus 1 theta times cos 2n minus 1 theta d theta. So this completes our proof for the second property as well. So this was beta function and its two properties. Next we will see the gamma function. The next function is gamma function. It is also known as the second Eulerian integral, and it is written as gamma n equals to the integral 0 to infinity e to the power minus x times x to the power n minus 1 dx, where this n is greater than 0. So this is the expression for the gamma function, and its properties are, the first property is gamma 1 equals to 1. This is easy to prove. We just have to plug n equals to 1 in this integral, and we can compute the integration and we will get 1. And the second property is gamma n plus 1 equals to n gamma n, which also equals to n factorial. So you see, this gamma function is an extension of the factorial function. So this sign you see here is a factorial function. This allows us to compute the factorial of a number. So let's say we need to calculate the factorial of 3. So we will write 3 factorial equals to, start with 3, multiply it with 2, multiply with 1, and we will write 6. So this factorial function only allows us to compute the factorial of integer number. The gamma function is an extension of this factorial function. This allows us to compute the factorial of rational numbers, the numbers that can be expressed in fractions. So let's prove the first property. Put n equals to 1, gamma 1 equals to integral 0 to infinity e to the power minus x times x to the power 1 minus 1, which is 0, and x to the power 0 is 1. So we can just write e to the power x dx. So the integration of e to the power minus x is minus e to the power minus x, and using those limits, now minus e to the power minus infinity plus e to the power 0 equals to, so e to the power minus infinity is 0 plus, and e to the power 0 is 1. So we got 1. So gamma 1 equals to 1. Now to prove the second property, all we have to do is write n plus 1 in place of n. So gamma n plus 1 equals to the integral 0 to infinity e to the power minus x, x to the power n plus 1 instead of n, and we already have minus 1, and dx equals to integral 0 to infinity e to the power minus x. This plus 1 and minus 1 will get cancelled, and we are left with x to the power n dx. We can also rewrite it as integral 0 to infinity x to the power n e to the power minus x dx. So to integrate this, we will use something called integration by parts, and its formula is integral u v dx equals to u integration v dx minus integration du over dx times integration v dx and dx. So we have to arrange these two terms in such a way that the second term is easier to integrate and the first term is easier to differentiate. Equals to, so keep x to the power n as it is, and the integration of e to the power minus x is minus e to the power minus x, and we have to use those limits, minus integration. Now the derivative of x to the power n is n times x to the power n minus 1 times, and the integration of e to the power minus x is minus e to the power minus x, and outside we have got dx equals to, we can keep this minus outside of the bracket, minus x to the power n e to the power minus x 0 to infinity. Now this negative sign and this negative sign will result in a positive sign, and we can keep this n outside of the integration as it is a constant n. Now integration e to the power minus x x to the power n minus 1 dx equals to, now if you use these limits we will get 0 here, plus n times, here I should have written 0 to infinity. Now if you see, this integral here and this integral here are same, so we can write gamma n in place of this integral, so gamma n, and we are left with n times gamma n. So this proved that gamma n plus 1 equals to n gamma n. So furthermore we need to prove that this also equals to n factorial. So we proved that gamma n plus 1 equals to n gamma n. If you see here, these two n's here are 1 less than this n plus 1. So you have n plus 1 in this gamma function, subtract 1 from this and it will result in n. So we can use this similar logic in this gamma function here and reach to n factorial. So let's do that. Keep this n as it is. Now subtract 1 from this n, we will get n minus 1, and write the same thing in the gamma function, n minus 1 equals to, keeping them as it is. Now subtract 1 from this n minus 1, we will get n minus 2, and write n minus 2 in the gamma function. If we continue doing this, we will reach to n times n minus 1 times n minus 2 times up to 1, which is n factorial. Therefore gamma n plus 1 equals to n factorial. So now we will see the relation between the beta function and the gamma function. The relation is given as beta m comma n equals to gamma m times gamma n over gamma m plus n. So to prove this, we will start with the beta function. So from beta function we know that beta m comma n equals to the integral 0 to 1 minus x to the power n minus 1 times x to the power m minus 1 dx. So we can use the integration by parts to integrate this. So the process is keeping 1 minus x to the power n minus 1 as it is, and the integration of this term will be x to the power m over m, and using the limits 0 to 1 minus integral 0 to 1. Now the derivative of this term will be n minus 1 times 1 minus x to the power n minus 2, and we have negative sign here, so this will make this sign positive, and the integration of this part will be x to the power m over m, and outside we have got dx equals to, so on using these limits we will get 0 plus n minus 1 is a constant, so 0 to 1 minus x to the power n minus 2 times x to the power m, and we can write this 1 over m in front, and we have got dx here. So we have left with, so now we have n minus 1 over m times the integral 0 to 1 minus x to the power n minus 2 times x to the power m dx equals to, we have n minus 1 over m. Now so when we integrate this again, we will get n minus 2 over m plus 1 times the integral 0 to 1 minus x to the power n minus 3 times x to the power m plus 1 dx. So this is what we got after integrating this one time, and this is what we got after integrating it second time. So you can see a pattern here. You see this term n minus 1, this is 1 more than this power here. So if we add 1 here, we will get n minus 1. Similarly, we have x to the power m, and the same m we have in the denominator. Similarly, we have n minus 3 here. So if we add 1, we will get n minus 2. And likewise, we have x to the power m plus 1, and this same m plus 1 is in the denominator. And the other thing is, if we add these two powers, we will always end up with m plus n minus 2. Add these two powers, we will get m plus n minus 2. So this is what we got after integrating it second time. So if we do successive integration, we will get n minus 1, n minus 2, n minus 3 up to 1. And in denominator, we will get m plus 1, m plus 2, and all the way up to m plus n minus 2. And we will get 0 to 1, 1 minus x. So if you see here, we have n minus 2. Subtract 1, we will get n minus 3. So we have 1 here. Subtract 1, we will get 0. So here it should be 0. And I told that these two powers should always add up to m plus n minus 2. So if this is 0, then the power of x must be m plus n minus 2 and dx. So the numerator term is n minus 1 factorial over m times m plus 1 times m plus 2 all the way up to m plus n minus 2. So here 1 minus x to the power 0 is 1. So we are left with x to the power m plus n minus 2. And the integration of this would be x to the power m plus n minus 1 over m plus n minus 1. And we have to use the limits 0 to 1 equals to, in numerator we have n minus 1 factorial. So here what we have to do is multiply the numerator and denominator with 1 times 2 times 3 all the way up to m minus 1. 1 times 2 times 3 all the way up to m minus 1. And we already have this term here. So times m plus 1 times m plus 2 all the way up to this m plus n minus 1. M plus n minus 1 equals to, so in numerator we have n minus 1 factorial, and this term here results in m minus 1 factorial, and denominator will result in m plus n minus 1 factorial. Previously we learned that gamma n plus 1 equals to n factorial. So this term here is 1 more than this n. So if we add 1 here, then we can write gamma n. If we add 1 here, we can write gamma m by, and if we add 1 here, we will get gamma m plus n. So this proves that beta m comma n equals to gamma n times gamma m over gamma m plus n. So this is the relation between the beta function and the gamma function. Thank you.